Hello, everyone, and a very warm welcome. So, what we are here to talk about today is time series analysis, right? Time series analysis has become a very important topic, especially when we talk about data nowadays, because a lot of data is associated with time. So, what we are going to understand today is what are time series and why do we need to do an analysis on that. We are also going to understand some basic components that we generally associate time series analysis data with. And finally, we'll also get to know when and when not to use time series analysis. We'll also understand briefly about a concept of stationarity, which is inherent to any kind of modeling that we do on time series data sets. So we are going to understand a basic concept of stationarity. And finally, we are also going to build our very first model. Okay, so first thing that we need to understand, why do we need to do time series analysis, right? We need to do time series analysis on data which has time as an essential component. Think of data related to stock market. When we talk about data in the stock market, we talk about, okay, stock market is starting at a particular time, let's say 9:15 a.m. and it's going to go ahead till let's say 3:30 p.m. and that has a time component attached to it. The same series repeats each and every day for every weekday. Generally, stock market is closed on Saturdays and Sunday. So there's a strong time component attached to this data. Similarly, if we talk about weather data, temperature, pressure, all of these things also get impacted by the season that is there, by a particular day. A particular day may be a very hot day, and again, how time is affecting the temperature will be different with respect to different seasons. So times weather data is also another very important data related to time series. And it's not just stock market data or sort of data on weather which is associated with time. If we talk about business processes, right, or if we talk about inventorization, if we talk about profits, revenue over time of the companies, then there's also a time component attached to it. And when we try to make out some analysis based on only this feature about the time component of the data set, then is what we call as time series analysis. So there are some very interesting use cases related to time series analysis. And for example, let's say you want to forecast how much profit are we going to generate in a company over, let's say, next 2 quarters. We have the historic record of a company, how much profit has the company generated over, let's say, the last 10 years, and now we want to forecast how much will be the profit in the next couple of quarters. Or for example, we want to predict how much products do we need to manufacture to meet the demand which is going to be there in, let's say, next year. Again, we can understand that by looking at a historical record and getting a better idea, because there's a demand and supply gap over there. If we produce more than what would actually be consumed, then we are incurring losses in terms of wastage. On the contrary, if we produce less than the demand, then again there's a problem, because we are missing out on potential customers. Our customers might go to our rivals. So there, it's not just that time series analysis is associated with weather data and stock market data, it's also relevant to our day-to-day problems in business. And getting time series analysis done also also helps us in understanding how we should plan for future, or how we should make sure that we are in best position to handle our business. Now, when we talk about time series analysis, there are certain things that we associate time series analysis data with. Let's say if we were to draw a sort of graph of a particular figure, let's say the sales of a company, right? Or let's say the number of clicks that a company is getting with time. If we draw time on x-axis and draw that component, for example, let's say if we draw time on the x-axis, and on the y-axis we have the sales of the company, which, let's say, go like this, right? Then what we can say is that generally, yes, there are a little bit of ups and downs, but generally we see that this price is going up. And that's what we mean by uptrending. That generally, let's say, the sales of the company are going up. If it's, this could be anything. This could be temperature, this could be stock market data, this could be the number of clicks, this could be the number or the amount of sales with respect to years. The common thing is that on the x-axis we are going to have time over year, right? That's the common thing when we talk about finding out these patterns. So when we say the market is generally going up, we say it is an uptrending time series. And similarly, let's say if the data is going down with time, we say it's a downtrending time series. And finally, if it's not going up, neither going down, then we say it's a stationary time series or zero trend time series. Now, seasonality is something which we associate with time, which goes up and down, changes with seasons. So maybe something like this. This could be a representation of a time series data set which shows strong seasonal components. A good example of a seasonal time series is, let's say, sale of ice creams. When we talk about ice creams, we know that ice creams are sold more in summers. So the sale would be high in summers and low in winters. So seasonal is something which changes with time. So sales of ice creams, or we can say winter clothing, or let's say summer clothing, or let's say cold drinks, all these things show some kind of seasonal pattern. The sales would increase or decrease depending on the season. Now there's another thing associated with seasonality, and that is cyclicity. Things which go up and down just like seasonal, but without any fixed pattern. So they may go up for some time, come down, then again go up very soon, and then come down, and then be up for a long, long time, and then come down. So cyclicity is patterns which also experience this up and down kind of behavior, but without a fixed time gap. The first time we saw a uptrend was, let's say, this much time, but the next time it took very soon to get us a upper point, and similarly next time also it was soon. The time after that it took a little bit longer, and then it took maybe even more longer. And similarly the length of these up periods was also different with each of these intervals. Now cyclicity is something in which the time is sort of not consistent, and that is something that we observe in terms of festivities, particularly if we are talking about festive sales in India. Now there's something unique which happens in India which is not there in many other countries, is our festivals, they change with each calendar year. With each calendar year, our festivals change in terms of dates. If we talk about Diwali, if we talk about Eid, they change with each year. So this time of period where a festival sale would be there also changes with time. But for example, if we talk about, let's say, the US, where most of the festivals are following a calendar year, for example, Christmas, Thanksgiving, and so on, in those scenarios, the festivals always occur at the same time. And yes, those could be better represented as a seasonal data set, things which are occurring regularly with time. Now, it's not just the products that we talked about earlier, ice creams, or let's say cold drinks, which follow a seasonal pattern, but also very complex product. Let me give you an example, and then probably you can tell me how seasonality affects it or how cyclicity affects it. I'm saying that cars, sale of cars also experiences some kind of seasonality. So what we generally experience with cars is that around the year end period, let's say in December, people generally don't tend to buy cars. And as an inverse, people tend to buy cars early in the year. Generally, when people buy cars, there's a registration date which is associated with that. And the registration is generally only mentioned in the year. So when, let's say, a certain person is trying to resell the car, that registration year decreases the value of the car a little bit. That's why people want to buy a car early in the year, so that the registration year does not have an effect on the resale price of the cars. That's a major reason why people tend to buy a car early in the year, and the sale of cars generally go down around November and December, because people want to get their car with the new registration year, so that the resale value of the car is also high when it comes to selling the car eventually. Okay, so we have talked about trending, we have talked about seasonality, we have talked about cyclicity, which is uh, products which are showing those that up and down behavior like seasonality without any fixed interval of time. And then finally, we have irregular time series data sets which do not show any pattern, whether going up, whether going down, or whether going up and down like seasonal data sets. They do not show any kind of pattern. Now, these are the very common patterns which we generally observe in our time series analysis. Let's understand, we know that there are a lot of cases when we can use time series analysis. Let's also understand where it would not be very helpful to use time series analysis. So any kind of data which does not vary with time, which does not have any relationship with time, and there's no benefit over there to apply time series analysis. If we talk about things like sinusoidal functions, right, which may sort of confuse us in thinking that those are seasonal patterns, but those are sort of a different way of showing functions, and it would not be very beneficial to apply time series analysis to sinusoidal functions, or let's say tan functions, or other mathematical functions. And similarly, values which are not getting affected by time at all, they are not showing any kind of pattern or are more or less constant. Again, it would not be very beneficial to use time series analysis over there. Now comes an interesting part. We are going to understand what is stationarity. Now, so far we were talking about the different components of time series analysis. We were saying that the time series could generally go up, which is uptrending time series. It could go down, downtrending time series, or it could be seasonal, going up and down at regular intervals, or for that matter, it could be going up and down at non-regular time intervals and be a cyclic time series as well. But in all the three scenarios, there was some change which was happening in the data with time. Now, stationarity is something which is a requirement for most of the time series models. This is an assumption that all the time series models make, that our data follows. So let's understand what is stationarity, and why is it that our models require our data to be stationary for us to give predictions on the data set. When we talk about stationarity, we mean data which more or less follows a constant mean. That means the mean does not change with time. So we were saying that for time series analysis, to be able to do time series analysis, we want the data to be stationary. And what we said is that by stationary, we mean that the mean, the average value of the dataset should not change too much with time. It should be more or less constant. And not just the mean, the variance in the dataset, how the data is changing, or the spread of the dataset should also be more or less constant. It should not change with time. And finally, autocovariance, which means the relationship of the value with itself. That means the dependent on, let's say, yesterday's value or day before yesterday's value. That relationship should also not change with time. For example, let's say if there's a relationship of 0.3, that's, let's say, a coefficient, that 0.3 value should also not change with time. So we are saying that the mean should be constant, more or less, variance should be more or less constant, and autocovariance should also be more or less constant. Now that's a little counterintuitive because we just talked about data which is trending, let's say our time series data. But if a data is trending, that means the mean value of the data is also changing with time. Let's say up till here, the mean would be maybe somewhere over here. But let's say from this point to the next point, the mean value would be somewhere over here. Again, if we look at the next bracket, the mean would change again. So the mean is not constant in a trending data set. Similarly, if we talk about seasonal data set, again, there is a change in mean which is happening over here. Let's say at this particular time, the mean would be maybe somewhere over here. And then if we are looking at this particular range, the mean might be slightly lower and so on. If you're looking at this particular range, then the mean is, let's say, somewhere over here. And if you're looking at this particular range, the mean is lower than that. That means even in seasonal data set, the mean is not constant as per the requirement. So that's a little counterintuitive that first of all, we are talking about modeling time series data set, which has trend and seasonal components. And then we are saying that we need the data to be stationary. The reason why we need the data to be stationary is because it's very difficult to model something which has a mean which is changing, a variance which is changing, and similarly a relationship with previous points which is also changing. And therefore, to make our lives easier, or therefore for the models to be making predictions in the right manner, they need us to meet these three conditions. But we don't have to worry. When we talk about trending or seasonal data sets which are non-stationary, we can still convert them to a stationary data set. So a stationary time series would be something like this, let's say with some kind of changes, not a lot of changes, but more or less the mean is sort of not changing with time. But the good news for us is that even though our data is non-stationary, we can still convert it to a stationary data set and then use time series analysis on that changed or transformed data set. So we will be understanding some of the ways later on how can we convert our non-stationary data set to a stationary data set. Before we decide whether we need to convert our data set to becoming a stationary data set, is first of all, we need to check whether it is actually stationary or not. And we need to check for the three conditions that we talked about earlier. The mean should more or less be constant, the variance should more or less be constant, and also the autocovariance, it should be more or less constant as well. Now, there are two particular approaches which are used to find stationarity, and they are both sort of complementary. That means it's not that we can use one and not the other. Both of them should be used actually, because none of them is perfect way. One approach is using an augmented Dickey filler test. It's a very famous test. It's a statistical test to test for stationarity. Now, the null hypothesis of this test is that the values are non-stationary. That means if the p-value of this test is less than 0.05, then we can say that we reject the null hypothesis and the values are stationary. So remember, the null hypothesis of this test, augmented Dickey filler, is that the values are non-stationary, right? That is the null hypothesis. And if we are able to reject that null hypothesis, then we would be able to say that the values are indeed stationary. Now, this particular statistical test largely takes care of the first, the constant mean, and to a certain extent the third condition about autocovariance. It still does not do a lot about constant variance part. And as a good practice, it's always good to make graphs to see the data set on the chart to see whether the values are stationary or not, right? So one thing is that to find out whether the mean is constant or not, we can draw a moving average or a moving variance on the plot to see whether the mean or the standard deviation or the variance, they are changing with time or not. So remember that ADF test is not perfect. It does not test for all the conditions, and it's always good to make a visual graph with time to understand whether the dataset is indeed following a stationary pattern or not. And we'll understand these things later once we do a demo of our problem. So now we were talking about a very famous model which is there for time series analysis, and that's called an ARIMA model. Now we are not going to go into very deep details of the model, but at least to get a basic feel of the model. ARIMA model is actually made out of two models. One is an auto-regressive model. So a model could just be an AR model. It does not have to be a REMA model, right? So it could just be an AR or auto-regressive model as well. The other is a moving average model. And if we have both these scenarios in place, we combine them and call it an ARMA model. So there's one model called AR, there's one called MA, which is a moving average model. The third is a combination of these two, which is called as ARMA model. Just a second, let me go back to the earlier slide. And actually, ARIMA model is just a minor modification of ARMA model. The I stands for integrated. And what we mean over here is if we want to internally in the model convert a non-stationary data set to a stationary data set. So there's something called as differencing, which we'll again understand better once we actually see a demo. And if we integrate that part itself in the modeling as well, then we say it's an ARIMA model or an ARMA model with D orders of differentiation. So we'll understand in detail on what do we mean by autoregressive, what do we mean by moving average model, and what do we mean by combining these two models. But autoregressive, as the name suggests, it means regression with itself. That means a relationship with itself, and we will understand that part in a little bit more detail once we go to the demo. And similarly, moving average, as the name suggests, we mean some kind of relationship with the noise part of the earlier day. So again, this is something that we are going to understand better on what this actually means. So what we are going to do now is we are going to go to a Jupyter notebook and understand how those three models work. And we are going to take a data set on the number of passengers taking an airplane. So initially when the airplanes came into picture, there were not many people who were taking flights. People were scared of taking flights. They were not as safe as they are today. There used to be many more air accidents, and people were generally scared about traveling in planes, and it was also overly expensive at that point of time. So we have a data set on how with each month the number of people taking planes changed over time. And the idea is to sort of forecast the demand of the number of passengers who would board a particular plane, and therefore let's say an airline can manage whether they can whether they should introduce new planes into the system or not. Or for example, a new market player who wants to start an airline, they can also get an idea based on the demand whether they should start a new airline or not. So we are going to have a data set on airlines, and we are going to try to run time series analysis data on that. So we have data in terms of months starting from 1949, January, February, March, and so on. And we have the number of passengers who took a plane in that particular month. All right, so with that, I'm going to move to Jupyter Notebook, and then we are going to implement our simple demo. So for this demo, what I'm going to do is not go into too much details of the code. That's it, because I get to know that you guys are sort of familiar with Python. The objective over here is not to go deep into the details of the code, but rather just to understand the basics of time series analysis. So without further ado, let's get started. So I'm going to load a bunch of libraries which we use for data analysis. I'm going to set up a few settings for making plots. I'm going to load the air passenger data set, and it's very important that when we have data set which has some sort of time component attached to it, is that we make our pandas aware that that particular column has dates in it, so that pandas can understand that format correctly. So there's a separate sort of class in Python called date, and we also want pandas to understand that a particular column has dates involved in that. And generally, when we have data sets which have dates attached to it, it makes a lot of analysis easier if we make that particular column as an index column. So if there's date associated with our data set, it makes a lot of sense to make that particular column as our index of our pandas data frame. So that is what I'm going to do over here. Make sure that the date column becomes the index. So over here we observe that the month column, which had dates in it, has become our index, and passengers contains our values of number of passengers in that particular month. So the first step that we said was that we want to explore the data set. So whenever you have any time series data set, or for example, even a data set which has time not associated with that, still the first step with analysis is exploring the data set. So let's go ahead and draw a plot on the data set. Now, just by looking at it, what do you guys think? Is it stationary or non-stationary? And you can use S for stationary in the comment box and NS for non-stationary. What do you guys think? It is stationary or non-stationary? It is non-stationary. It is changing with time. If we try to draw an approximate sort of mean over here, we see that it's going clearly up. So definitely non-stationary. Observe that there's also some kind of seasonality attached to the data set, right? And can you guess why are we getting seasonality in the data set on air passengers? During, let's say, the middle of the year, maybe there are summer vacations or maybe there are winter vacations, right? Whatever it is, during vacations, people tend to travel with their families on holidays, on trips a lot more compared to non-vacation months. So during the period when there are vacations in schools, that is when people like to travel a lot, and therefore we see a strong seasonal pattern in the number of air passengers on this data set. So all right, we observe that this data set is one, non-stationary. That means we cannot model it directly, and second, it also has some seasonal component attached to it. Now, this is what I meant by moving average earlier. What we are going to do is we are going to use pandas to create a moving average, and we are taking a 12-month moving average. Remember that the data that we have is sort of monthly data set, and what we are going to what we are going to do is we are going to say on our index data set, which is indexed by month, we want to take a rolling mean of 12 days. We can change these days, but right now we are going with 12 days. And what we want to do is we want to get a mean over here. And similarly, later on, we want to get a standard deviation. So let's look at these and then we'll understand what do we mean by moving averages as well. So this is what we mean by a moving average. Let's say these are the first few values of 12-day moving average. The very first value, 126.66, is going to be the mean for the first 12 values. Now we observe that the first 11 values have not a number over here. The reason is because when we are taking out mean for the first 12 days, we did not have data for the 12 days initially. Therefore, the first 11 values are not our numbers. Similarly, when we talk about 126.91, it would be a mean of the next few values. So in fact, let me also get the head of the original data set over here so that you can understand it a little better. Let's have our roll mean dot head 20, and let's also have our index data set with, let's say, a head of 20 again. So when we talk about the first value 126.166, right, that's the first value we are seeing in our rolling mean. That is a mean of the first 12 values of the data set. So that is the mean of the first 12 value of the data set. Let me just clear the drawings. And okay, so I think this would be better to explain. So when we talk about the first value, that is the mean of the first 12 days of the data set. That is the value which we are getting over here. So the first value that we are getting is actually for the December month of 1949, because for all the other values in the beginning of the dataset, we don't have 12 values to begin with. Now, when we talk about the mean for the next value, that is going to be for the next 12 values. And similarly, when we talk about the next value, that is going to be the mean for the values which are next 12. So starting from 132 up till 126. And similarly, this 12-day period will keep on rolling one step at a time. So the next value will have mean from 129 up till 141. The next one will have a mean from 121 up till 135, and so on. And that's why the name rolling, because the mean is going to roll over time. We can choose the window that we want to keep in the data set to roll for taking out the mean or for standard deviation as well. So we have the rolling standard deviation and the rolling mean as well. So moving ahead, now what we are going to do is, we said that we need to plot our graphs, although we can visually make out that our data set is clearly non-stationary, but we want to also plot our rolling mean and our rolling standard deviation to see and to confirm whether the data is stationary or not. So in blue, we have the original data set, and in red, we have the rolling mean, and in black, we have the rolling standard deviation. Observe that the standard deviation started from very close to being 0 and ended up at being very close to 100. So standard deviation is changing with time, which is not a good thing for us. And similarly, if we talk about the rolling mean, the 12-day mean, we also observe that it is clearly going up. So changing with time, that means clearly non-stationary. Also observe that both standard deviation and rolling mean graphs are starting at a different point compared to the blue line. That's because we are taking a 12-day rolling average. We don't have the value for the first 11 days for the rolling means. That's why we don't see a value over there in terms of the red and black lines. Okay, so we have plotted our original data set, and now this is a very clear representation of the data being non-stationary, right? It's clearly changing with time, the mean value and the standard deviation. So clearly a non-stationary data set right now. So right now, this is the visual way of checking whether the data is stationary or not. We also talked about a statistical test, which is going to help us do the same thing. So we are going to import that statistical test augmented decay from, let me correct the spelling over here, from stats models library, and we are going to understand what the output of the result is as well. So generally we get a set of outputs with decay test. The first one is the test statistic. And actually we're not going to go into too much detail about the test statistics and other things. The main thing that is of interest over here is the p-value, right? Or the significance value. What we want to know is this value should be less than 0.05, right? That's what it should be less than. It is clearly very, very high. It's 0.99. So clearly not less than this. That means the data set is non-stationary. We cannot reject the null hypothesis. So these values actually represent what the critical value or what this test statistics, the first value, should be for this value to be a stationary data set. So at 5% significance level, that's the significance level that we are checking, the value should be minus 2.88, but it is actually positive 0.81. So it's quite different from what it should have been. So this is what we mean by critical values. If we want to make or reject our null hypothesis at a 1% significance levels, then our test statistic should be lower than minus 3.48. So this is how we can understand these the statistical test. But the main thing which we should generally focus on is the p-value. If it is less than 0.05, then that tells us that the value is probably stationary. Okay, so now we said that there's a visual way and there's a statistical way. What we are going to do is we are going to wrap both these methodologies into one function called test stationarity, and we are going to put our Dickey-Fuller test as well as our plotting into the same thing so that this gives us both the things in one go. So we are going to run this function and just try this function on the data set that we are working with. The good thing with this is that we get the plot as well as our statistical test right in one place, and we don't have to copy paste that hefty piece of code each and every time. We have wrapped it in a nice function which we can reuse several times now. Okay, now we got to know that this data is clearly not stationary. We now need to convert it to a stationary data set to undergo time series analysis. And there are quite a lot of ways, and actually we can convert a non-stationary data set to a stationary data set. So one way is to take the logarithm of the data set. Another popular approach is if we subtract the simple rolling mean, or if we subtract the exponential rolling mean, that's also something which can give us a stationary data set. Or the most popular way of converting the data set into stationary is subtracting each value with its previous value. That's also something which gives us stationary data set. And lastly, but not the least, we have seasonal decomposition. So completely transforming our data set into the different components which are there in the data set. That also helps us in giving stationary data sets. Now, in real life, for most of the data sets, this technique works. So in most of the data sets in real life, if we subtract the value with its previous value, so if we subtract today's value, let's say at time t, with the value at time t minus 1, yesterday's value, and similarly we do it for each and every day, that is one of the most popular way of doing things. And in most of the real life data sets, that is going to solve our purpose. But that said, there are some cases where we need to do complex transformations, we need to take logarithms, or we need to combine multiple of these methodologies so that we can convert them to stationary data set. Now, because this is a sample data set that we are talking about today, this data set is a little more complex and we would need to do multiple transformations on this data set to make it a stationary data set. So we are going to apply these techniques one by one and see whether they make our data set stationary or not. We are first going to start with log. We are going to take a log of the values. Let's take the log of the values over here. So actually this is how the values look like if we take a log, looking at the plot, stationary or non-stationary, S or NS. Okay, so clearly we see that the mean is still changing with time. Taking a log over here did help us to smoothen the data set a little bit compared to earlier. So this is how our graph was looking earlier. Observe that we were getting bigger and bigger high points on this data set earlier, but at least by taking log, that problem has been solved. So now in the data set, these uptrending periods are not increasing with time. They are more or less very consistent. So at least some sort of cleaning has been done on the dataset by taking the log values. Now on this dataset, what we are going to do is we are going to further change these logged values. So we are not going to start with a beginning, but we are first going to continue with the logged values and then try some of the other methods in combination. So for the logged values, now we are taking out the rolling mean, and then we are going to subtract this rolling mean from our log values to combine the two methodologies and then see if the dataset is stationary or not. So in the first step, what we are doing is taking the rolling average. In the second step, we are subtracting the log values with the moving average values, and this is what we get after we subtract the values, the logged values with the moving average values. Let's again check our test stationarity function on this dataset now. So now you have the graph in front of you. You also have the p-value in front of you. It's stationary data set now, right? So now more or less the mean, which is in red, is not changing too much with time. Now remember, we would not worry about these small changes which happen, because more or less it does not have to be very constant, but more or less in a narrow range is sufficient for us. Similarly, with standard deviation in black, we again see it's not changing too much with time. Also, if you look at our p-value, that is also less than 0.05. It is 0.02. So clearly it has become stationary now. Okay, but just for completeness, we are going to check some of the other methods as well to check whether the data is stationary or not. So earlier we tried to remove or difference the simple moving average. We are this time trying to remove the exponential moving average, and I'm going to go through these methodologies fairly quickly now. So let's say if we do that, and then if we, let's say, test for stationarity this time, then again we see that this methodology also gives us a stationary data set. So if instead of subtracting a simple moving average, if we subtract our exponential moving average, that is also creating a stationary data set for us. Another way that we talked about is if we select the previous value and we remove the next value from that, that is also one of the most important ways. And this time we are going to try that with log. To do that, we need to use a function shift in pandas, and that is going to help us in removing or subtracting the previous day value from the current value. So this is what we get if we subtract one day value with the previous day value. For example, just to explain it to you on how it would look like. So this is our original logged data set, and now if we are looking at the data set that we have changed. So what we are doing in shifting is we are just subtracting the previous value from the current value. Now for the very first instance, there is no value before 4.71. That's why we get a not a number over there. For the next value, which is for the month of February, we get 0.052, which is nothing but the difference between 4.77 and 4.71. Similarly, if we talk about the value after that, that is also 4.88 minus 4.77. And similarly, if we talk about the next value, this is 4.85 minus 4.88, and therefore the negative sign over here, 4.88, is bigger than 4.85. So that's what we mean by differencing, subtracting the value from the previous value. Okay, So let's go ahead and test this stationarity on this data set as well. So again, okay, so this has not actually done a complete stationarity for us so far, because we see that the p-value is slightly more than 0.05. So it has not done it, at least in this one particular step. Now, the good thing with differencing is that we can difference it multiple times. We can use differencing several times to make our dataset stationarity. Right now, we did it just once, and for now, we are going to ignore this part or this slight non-stationary component in the dataset. And finally, we are going to use a tool which is available with us in stat model of seasonal decomposition. So this is also a very nice tool. We are not going to use it for now, but just to showcase on how it works. So on the top graph, we have our original data set. And in the graph after that, we have the general trend of the data set. So the seasonal decomposition separates out the trend from the original data set, also separates out the seasonal component from the original data set. So in a way, you can think that if we add these two graphs, we are going to get this top graph. And that is what seasonal decomposition has done. It has separated the seasonality part of the data set from the trending part. So this is a very nice tool to sort of make our data set non-stationary. If we remove both these parts, the seasonal part and the trending part from the original data set, then we get the last particular kind of graph, right? So this is what is remain. This is what remains in the data set if we remove the trend and if we remove the seasonality part of the data set from the time series. And remember, we don't have to go into deep level of concepts right now. Remember, this is just an appetizer and sort of just a way to give you a brief idea about how things work in time series analysis. It's a very complex topic and requires fair bit of time. So don't worry, once you actually go through the course, we'll be going through these things in a lot more detail. All right, so this is another way that we found can be used to make our dataset stationary. Okay, we have got to learn about five ways in which we can make our non-stationary dataset stationary. And let's say we have done that. Now we want to understand what is ARMA modeling. So when we say auto-regressive or AR model, what we are looking for is a relationship of today's value. Let's say I'm using the word P for price. What we mean by AR1 model, we are saying that today's price has a relationship with yesterday price. So that's we are saying price at time t for today has a relationship with time yesterday. That's what we mean by auto-regressive model. And we generally decompose it into three things: the mean of the data set, and there's some coefficient like a simple linear equation gamma 1 over here, and we are saying it's the price of yesterday, and then there is some noise or error. So this is what we mean by auto-regressive model. The model has certain relationship with the price of yesterday. Now this is an auto-regressive model of order 1. If we say that the relationship is also not just with yesterday's price, but day before yesterday price as well, then we say it's an AR2 model. In this time, we are going to have a relationship with yesterday's price as well as day before yesterday price as well. And similarly, we can have an AR3, AR4, AR5 model as well, in which the relationship is with 4 days earlier, 3 days earlier, 2 days earlier, and so on. Right. So this is what we are looking for. This is the kind of relationship we are looking for in auto-regressive models. Not all data sets, not all time series data sets are going to show this model to us. So it's not that this is going to work in all time series, but there are different orders which could work in different data sets. Now, very quickly, moving average model is something in which we say that the price today has a relationship with the noise that we were just talking about of yesterday. So if we say the price of today has a relationship with the noise of yesterday, that's what a moving average model is. So in this data set, we again have the mean component, relationship with the noise of yesterday, and then we have today's noise as well. Similarly, if we talk about the moving average 2 model, it has relationship with day before yesterday's noise as well and yesterday's noise as well. And similarly, MA3, MA4, and MA5 model will have relationship with the noise of earlier days. Again, remember, we are not saying that all the time series are going to have a moving average model, but some of them might have a moving average model application in that dataset. Now, ARMA model is auto-regressive moving average model, quite simply a combination of those. And it is represented in two orders. The first value is for auto-regressive. So this is a one order of auto-regressive and a two order of moving average. Again, a one order of moving average model. So in this, we are saying that the relationship is both with yesterday's price and yesterday's noise as well. So that's what an ARMA model is. And similarly, if we say ARMA 1-2 model, yesterday's price, but both yesterday's and day before yesterday's noise. And similarly, when we say ARMA 2-1 model, the inverse of the opposite one, we have relationship with both yesterday's and day before yesterday's price, but only yesterday's noise. So this is how we can depict an ARMA model in two orders. The first order corresponds to the moving average, sorry, the autoregressive, and the second order corresponds to the moving average order, or the number of lags at which the relationship exists. Right now, the relationship only exists in one lag, and in this particular case, the relationship exists with two lags, and so on. Okay, so on that note, let's actually start in running our model. Let's start to reach closer to running our model. But before we run our model, we need to know which lags is our relationship showing. Is it showing relationship at two lags, at autoregressive, one lag for moving average, and so on. Now, there are quite a lot of ways in which we can find out the number of lags for which we are looking our relationship at. One is by plotting something called as autocorrelation and partial autocorrelation functions. Now, this method is not a great method. It works only if there's either an AR or an MA model. It does not work when we have both AR and MA model, or if we have an ARMA model. And generally, if we have an ARMA model, the better thing to do is try out different combinations of these models and choose the one which is performing the best. Now, we don't have to do it manually. Again, there's a great tool in statistics or in stats models which can help us do that. But essentially what this tool will do is try and run several different order combinations on the dataset and tell us the one which is the best performing one. So let's say if we run that on our dataset, and now from now onwards, what we are going to do is we are going to run the dataset which is logged and then differenced. So do remember that it was not perfectly stationary, but we are ignoring that part and still running our model on that particular dataset. So we are running our model which is logged as well as differenced ones. So that means we have first taken a log of the values and then taken a difference between the previous value for each and every value. Now, when we ran this tool, we get that the best order that we should use is a 2,2 order. That means a relationship with two lags of autoregression, a relationship of two lags for moving average. Okay, so now that we have got to learn about it, let's try and run our ARMA or ARIMA models. Now, if you remember when we were talking about slides, we were talking about that there's an ARIMA model which is not very different from ARMA model. It just adds one component. If we want to difference our data set, then we can do it within this model as well. If we want to take difference of the data set one time or two times or three times from the previous values, we can use the I part, the integrated part of that as well. Now, the way we represent ARIMA model is slightly different. We say that the first value is the order of the AR model. The third value is the order of the MA model. So in ARMA model, there were only two values, P and Q. Over here, the P is the first value and this is the last value. And then there's the middle value D, which tells us the number of times we should take difference from the previous values. So we are going to import an ARIMA model from stat models and then instantiate it and fit it on our dataset. Although we found out that we should use a 2,2 model, we are actually first of all running a only AR model. We are using 0 for the moving average. Remember, the middle value is for the differencing. So we are saying in this dataset, we want to difference the dataset once. So we are using an order of 1. And in the title of the dataset, we are also getting a value of the difference between the errors. So to get an approximate idea of how good our model is, the lower the value, the better it is. So let's say, even though we know that it should be a 2,2 order, we are running a 2,0 order over here. Let's see how it performs. So in the red, we see our predicted values. They seem to be a little different from our actual values, and the error that we are getting in a way is 1.5. Okay. Now let's try to run an only moving average model. Let's try to change the order to 0, 2 and then see if that is better. If we are running a 0, 2 order, we are getting a root mean squared error of 1.4. So slight improvement from 1.5 earlier, but not really as great as it should have been. And finally, we are going to run the model which was suggested to us by the tool earlier. Let's see if this performs better. Okay, so this indeed does perform better. The error is 1.02 compared to 1.47 earlier. So this tool that we used is quite reliable to find out the best sort of order of model possible. If we just want to extract the prediction values, we can use an attribute fitted values, and we are going to get predictions of our data set. But here comes the tricky part. Remember, we converted our original data set to make it stationary. We first took a log of the values, and then we took a difference from the previous values. Now that means the predictions that we are also getting are in the transformed data set. These are not representing the actual values. We ran the model on the transformed data set, so the predictions are also in the transformed form. To get them back into the original form, we need to follow a few mathematical procedures. The last thing that we did was that we took out the difference between the values. If we want to negate that part, we need to take a cumulative sum of the values that is going to give us the values back in the original form. So if we take the cumulative sum of these prediction values, we are going to get this set of values. We are going to add them to the very first value so that we can get them in a form which is very close to the earlier form. But again, there's a problem. Remember, we used two transformations. We just did not do a differencing. We also took a log of the values. So earlier we took a log of the values. Now to convert these values to its original form, we are going to use an exponential function over here to get the dataset in the original form. So we are going to convert this dataset into its exponential form and then check the original dataset versus the predicted dataset. So running our model, this is what we see over here. In blue, we have our original dataset, and in orange, we have our predicted dataset. Now, as you might be observing right now, this does not appear to be that great. Yes, the good thing is that it is showing the movements in similar directions. So when our original data set is going up, our predictions are generally also going up. And when our data set is going down, original data set, then our predictions are also going down. But we also see a gap, a significant gap over here as well. And there are a few reasons why we are observing these gaps. One is that we did not make sure that our data is stationary before running our model. Remember, the p-value was 0.07, but we ignored that part and still ran our model. Second is we are running a very simple model as of now. We are only running the model with the time series data set. Now there are other ways like adding more feature, additional information about the number of passengers. Like for example, if we say, let's say we assume that this data set is for the US, maybe the GDP of the country or of US in those years, maybe how fast a country is growing can also get us an idea about how many passengers are going to be traveling by planes. Maybe we can also have a feature on the number of people who have a wealth or who have earned more than, let's say, $500,000 in a year, right? That can also sort of give us an idea about how many passengers are going to be there in next month or next year. But right now, we have not taken a single additional feature, but only running data set on the parent data, only running the model on the parent data set. One additional thing is that our data set has a strong seasonal component attached to it. And when we talk about seasonal data sets, there are different models that we need to implement. They're actually called as SARIMA models, so which incorporate seasonal part in the ARIMA models as well. So SARIMA models are the ones we should use for seasonal data sets, but we went ahead with a simple ARIMA model. And once we add more features, the model that we call is called as a SARI max model, right? The X represents the extra features that we are adding apart from the original data sets. Okay, so what we have done so far is we have got a basic feel of time series data set. What we did was we imported a data set, checked whether the data set is stationary or not, used some transformations on the data set to make it stationary. We still went ahead with a dataset which was not completely stationary, and then we went ahead and found out the right number of lags for autoregressive and moving average models that we should use while modeling. Then we went ahead and ran our model with the right order, and then we are looking at predictions, right? So this is what we have done in today's session so far. We have got a basic feel of time series analysis, the kind of things that we can do with time series analysis. We have got to know a basic idea about stationarity. We also have some intuition about how to convert a non-stationary data set to a stationary data set, and in a very sort of crude way, we have also ran our first time series model. Of course, this model can be improved further by using more complex models, but at least now we know how to run a basic model. All right, so that's actually it about time series analysis. What we have done is we have understood what are time series data sets. We have understood the basic components which we generally associate with time series analysis, trend, stationarity, cyclicity, irregularity, and we got to know the basic concepts of stationarity, and then we have ran a basic ARIMA model on a data set on the number of passengers with each month in a particular country. All right, so on that note, goodbye and take care.